A smart city concept symbolizes an integration of information and communication technologies, ICT, with all aspects of urban life. In this work, we are interested in environmental and climate components of smart cities, especially in remote areas with harsh climate conditions. Several international projects stimulate efforts to develop ICT approaches to urban environmental management, climate change adaptation and mitigation in the Arctic cities. Smart cities act through more sustainable organization and management of urban spaces. Physical space is organized in green, blue, white environment and together with its microclimate becomes integral component of a smart city. Information and communication technologies offer solutions for more efficient interconnection of urban services, critical infrastructure and, as it is important for us here, for real-time environmental monitoring, modeling, and climate change assessment. Although the environmental component of smart cities is still underdeveloped, it has become clear that an optimal smart city methodology for environmental monitoring and projection must fuse diverse observational networks, high-resolution, low-latency satellite data, and an Urban Integrated Modeling System, UIS. To cover the recognized knowledge gaps, smart cities must possess a variety of decentralized but integrated observational networks. Smart cities must rely on high-resolution models and information analysis systems. Those tasks essentially rely upon the Internet of Things and high-performance and cloud computing. Typical environmental problems for the smart cities are quality of human environment, air pollution, local perspectives of global climate change, urban ecological services, etc. A critical and popular indicator of smart environment is given by urban temperature anomalies. In the Arctic cities, surface temperature anomalies or the surface urban heat island are important to characterize climatic effects and risk in the city. Analysis of satellite observations from moderate resolution spectroradiometer MODIS over 2000-2019 indicates that almost all Arctic towns, even small ones, exhibit considerable heat island of +1 to +5 degrees. An important consequence is vulnerability of the Arctic cities to ground deformation and hydrological risks. In practice, almost all Arctic urban policies underappreciate the local environmental and climate impact, focusing on more distant and less urgent climate change issues in their climate action policies. Persistent urban warming anomalies are comparable to the global warming anomalies expected to take place in several decades in the future. Dense monitoring systems are needed to manage the urban environment. Arrays of inexpensive sensors connected through Internet, the Internet of Things, could be deployed to monitor local anomalies of temperature, wind, precipitation, icing, and many other parameters. For demonstration of the approach, we have deployed the Urban Heat Island Observational Network, UHIARC, in 5 Arctic cities. Here is an example in Nadim. Additional instruments allowed for better characterization of the 3D structure of the urban environment and provide for initialization of urban digital twin models. Since urban environmental anomalies are highly localized in space, high-resolution models are needed to simulate urban winds, air quality, and other potentially hazardous phenomena. We have already demonstrated and published on an added value of turbulence permitting modeling in another Arctic city of Apatite. The model PALM was able to simulate a meandering turbulent flow from an industrial zone towards residential area. sometimes something which coarser resolution models fail to predict. As surface roughness is one of the most significant factors affecting the flow direction and turbulent diffusion, such scenario modeling has a significant potential for nature-based solutions for the Arctic towns. Organization and allocation of physical space in smart cities is a powerful instrument to manage the urban environmental quality and climatic risks. Rearrangement of green-blue-white space in the cities might reduce adverse consequences of the urban heat island. In the Arctic, the urban anthropogenic heat fluxes are responsible for early snowmelt, as seen in this satellite image, for ground thaw and shift of phenological seasons. Sustainable Arctic settlements demand detailed environmental information for informed policymaking. Information and communication technologies open for development of urban digital twins, a fusion of diverse smart observational networks, analysis algorithms, and integrated environmental models. A design of such an integrated approach, its philosophy and methodology are in focus of international projects CERUS by the Belmont Forum and Ursa Major by the Norwegian Research Council.